So this talk will be about the NP-Hardness of circuit minimization for multi-output functions, and this is joint work with Bruno Loff at the University of Porto and Igor Oliveira at the University of Warwick. So just before we begin, I want to address whether or not you should be watching this specific talk. There are actually 3 talks available online, each with a slightly different niche regarding this work. So I made a little matrix. So the first talk was a TCS Plus talk that I gave. There's obviously this talk, and Bruno Loff gave a talk at HSE's TCS Lab seminar. And so how I would distinguish them is like this. I think if you're maybe not so familiar with MCSP or want to hear more about the background of MCSP and what are all the connections that make MCSP so interesting, I think the TCS Plus talk spends a lot of time on that. While this talk and Bruno Loff's talk, although we obviously go over all the definitions and you don't need to know MCSP ahead of time to be able to understand this talk, but we spend less time on background and going over all the possible connections. So I think if you're interested in that, maybe the TCS Plus talk is good. On the other hand, if you want to know the details of our proof, I think the TCS Plus talk has the lowest amount of details on the proof. I think this talk has a medium amount of details, and Bruno Loff's definitely has the highest amount of details. He gives the full proof, all the details, all the good stuff available in that talk. And of course, they have slightly different lengths, so depending on how much time you have, different talks might be better. But that's the overall summary there. So with this talk, it's going to kind of break into 3 different parts. In the first part, I'm just going to define MCSP. What is it? Why should you care? That kind of stuff. Then I'm going to talk about the history of the problem, what kind of prior work there was, why is it difficult to show MCSP as NP-Hard. And I'm going to talk about some recent development that was an important ingredient for our result. And finally, I'll define this multi-output circuit minimization problem. I'll say what it is, and I'll talk about how we're able to show it's NP-complete. Okay, so what is this problem called MCSP? So MCSP stands for the minimum circuit size problem, and it takes 2 inputs. The first is the truth table of a Boolean function. So that's just the list of all the values the function takes on all of its inputs. So it's just some string here. And also some size threshold, S, which we can write unary. It actually doesn't matter so much, but I put unary there. And the output is going to be, does there exist a circuit with at most S gates computing this function F? And to be absolutely precise, you need to specify exactly what model of circuits you're dealing with. For us, it's just going to be the usual and or not fan-in-2 circuits. So that's MCSP. And what do we know about the complexity of MCSP? It's kind of a bit of a mystery. Indeed, it's pretty easy to see that MCSP is actually an NP. Basically, if you want to witness a yes instance MCSP, you can hand over the circuit of size at most S for computing the function. And because you're given the whole truth table as part of the input, you can actually go in and check whether or not a purported circuit actually evaluates to T. So that's why it's an NP. The natural question is, could it be in P? It turns out probably not. There's this connection that says if MCSP were to land in P, then cryptography as we know it would break. So it's probably not there. And so it's likely some problem that's in NP and not in P. So the natural question is it NP complete? And this is a big open question, and I'm going to talk about it a lot more later on. But the answer is we don't know. If you ask me, I think it's NP complete, but researchers are divided on the topic. So I've told you what MCSP is, and the rest of this talk is kind of about a result that's trying to help us understand MCSP. So, it might be good for the viewer to say why we care about this problem. Why do we want to understand it better? And I'm not going to be able to say too much about this, but at least for me, what I think is so interesting about MCSP is the connections the problem has. It's connections to cryptography, connections to learning theory, and seeing as this is a complexity conference, connections to stuff we love like structural complexity, average case complexity, and circuit complexity. And I just want to illustrate a couple of the connections here, just very briefly. So we have these connections which take this form. If something is true about MCSP, if we learn some fact about it, then we get a solution to a long-standing open problem. And so, for example, if we were able to show that MCSP is NP-complete, this open question I mentioned earlier, then by a theorem of Murray and Williams, we would get a breakthrough complexity class separation. We get that X was not equal to ZPP. On the other hand, if you're able to show that like certain approximations to MCSP are NP-complete, then by a really cool theorem of Hard from a couple of years ago, you get that computing NP on average is actually as hard as computing NP in the worst case, for some notion of average that I won't be able to cover in this presentation. Finally, if you could prove like barely superlinear circuit lower bounds against some version of MCSP, then by a theorem of hardness, a hardness magnification theorem of McKay, Murray, and Williams, you get that all of NP does not have polynomial size circuits. So in all of these cases, you have like some interesting question about the complexity of MCSP, and it's connected to these interesting open problems in various different fields. And so to me, that's why I think MCSP is very interesting. And if you want to hear more about these connections, as I mentioned earlier, I spent a couple minutes talking about each of them in this TCS Plus talk. And so you can hear about it there. So is MCSP NP hard? This is kind of like the question that motivated this work. And I said, at least I think the answer should be yes, but this is like a long-standing open question. In fact, it's kind of like one of the, perhaps like one of the longest standing open questions in the theory of NP completeness. It said that Levin actually delayed publishing his work on the theory of NP completeness, his original work, because he wanted to capture MCSP in the framework. He wanted to show that MCSP was NP hard. And, you know, even to this day, we still don't know whether it's NP hard. So maybe it's good that Levin decided finally to publish this thing without MCSP. What we do know now is we have these formal evidence that it would be difficult to show MCSP as NP hard. In particular, there's this quote that Ryan Williams gave in a Simon's talk. If it is NP complete, it would have to require techniques that are not like any polynomial time reduction we have ever seen. And so why is Ryan saying this? I kind of want to give the intuition here. So let's just review the definition of MCSP really quickly. So in MCSP, you get this function and this size parameter, and you're supposed to output yes if the complexity is less than s and no if the complexity is greater. So what that means is, if you look at the difficult no instances of MCSP, the ones that like aren't easy to brute force, what they're corresponding to are functions requiring large circuits. And if you're going to give a reduction from SAT to MCSP, you probably have to map the difficult no instances of SAT to the difficult no instances of MCSP, which means your reduction, if it was deterministic, is kind of inherently providing a way to produce functions requiring large circuits deterministically. And this intuition can be formalized and it's been formalized in various theorems, which basically have the takeaway that being able to prove a deterministic polynomial time reduction between SAT and MCSP would require a breakthrough. And so what does this mean? Does it mean that like it's hopeless to be able to try and prove MCSPs and NP hard? Maybe like we just need to come back to it when we have better techniques. To me, at least, I see like two holes in this. The two holes, I think, are one, this polynomial time reduction. Like, what if you're able to use sub-exponential time reductions? Like, maybe you could do something a little bit better. In fact, I strongly believe that the exponential time hypothesis should imply that MCSP is not NP, and that this should be provable with current techniques, like gate elimination and stuff like that. And the other thing is this deterministic part. So kind of like the difficulty in getting a reduction, as I've explained it, is that you'd have to be able to somehow deterministically produce a function requiring large circuits. And that's something we don't know how to do. But if your reduction was randomized, then it's not clear what the barrier should be, because we know that a random function is going to require large circuits with high probability. So maybe you could get a randomized reduction to work. And, as far as I know, there are no known barriers to getting a randomized reduction to work. And this is kind of the approach we take in our result. So in fact, there have been some prior works that also try and use randomness to escape the possible barriers to showing that MCSP-like problems are NP-hard. In particular, there's this work earlier this year that showed some Oracle variant of MCSP is NP-hard using randomized reductions. And to me, this result really seems to speak to the power of randomized reductions in proving hardness for MCSP, because there's this result. It's basically the same result that Murray and Williams showed. If you look at their logic, not only does it apply to MCSP, it applies to Oracle MCSP. And what that means is, while we're able to use randomness to show this problem is NP-hard, if we got a deterministic reduction for this problem, then that would yield x not equal to ZBP. So I think, to me, this is good evidence that at least randomness gives power. Maybe randomness, might not be useful for MCSP, but at least for these like very close variants of MCSP, it could be useful. And let me now define what exactly this Oracle variant of MCSP is, because it's going to be an important ingredient in some sense in our proof for multi-output MCSP. So Oracle MCSP is going to be defined as follows. It's going to take 3 inputs. The first 2 are the same as MCSP. You have this truth table T, which has, is just represented by a string, and it's the function you kind of want to minimize, same as before. You have this input size threshold S, same as before. And finally, the thing that's different is get the truth table of an Oracle function. So this is just some function that you're going to be able to get as an Oracle in your circuit. In particular, you're going to output, does there exist an O Oracle circuit computing T with at most S wires? So now in your circuit, you're allowed to use this O Oracle in order to compute O for basically free in order to try and compute T. So you can think of this as kind of like a conditional version of circuit complexity. How hard is it to compute T relative to this Oracle O? And just to give you a high level idea of how this reduction works, it goes from set cover to Oracle MCSP. And so when you're given a set cover instance, S1 up to SM, that covers the ground set N, what it's going to map to is a random function. I'm not going to tell you how many bits this takes as input. I'll suppress all those little details. And oracles. Now, as it's defined, Oracle MCSP only takes 1 oracle as input. But just to make the intuition for this proof easier, I'll say there are multiple oracles. So there's multiple oracles, T sub S1 up to T sub SM, that are kind of induced by the set cover instance. So this function T that actually has no dependence at all on the set cover instance. It's just the oracles. And how are we going to construct these oracles? I'm not quite going to say how they're constructed, but I'll tell you what property they're going to have, which should give the intuition. It says that whenever you look at some subset of the set indices that is a cover of N, so maybe the first 3 sets cover N, so this could be 1, 2, C could be 1, 2, 3. If you look at the OR of these Oracle truth tables on that corresponding cover indices, that's going to OR together to give you T. So kind of how these T sub S1 up to T sub SM are constructed is they're kind of like masks of T, where the masks are in some sense corresponding to these sets. But it has this property that the covers in the set cover instances correspond to OR circuits for T using the oracles. And so kind of by construction, what you get is that if you look at the optimal set cover size of S1 up to SM, that needs to be at least this kind of conditional oracle complexity of T relative to these oracles, because you could just OR together the oracles in order to compute T if you had a set cover. So that gives the lower bound. And actually what they show is that this is approximately that, and that's what gives the NP-Hard result. So not this like kind of naive upper bound can't be too far from optimal, and so that shows Oracle MCSP as NP-Hard. And we're going to use these ideas in our reduction. So now let me talk about our results. So the main result that we have, and in fact the only one I'll talk about in this talk, is that MCSP for multi-output functions is NP-complete under randomized reductions. And so let me now define MCSP for multi-output functions. Now you get a truth table of a multi-output function. So you can view these as like single bit output functions that are like concatenated together, and then you look at the concatenated truth table and some size threshold S. And you're going to output, does there exist a circuit computing this multi-output function with at most S wires? And yeah, I just want to define what exactly I mean here by a circuit computing a multi-output function. So this is what I mean. I'm going to say a circuit C, like this one, computes this multi-output function F if for each component of F, so you can define F sub I to be the ith output of F, if for each one of these like component functions F sub I, there is some specific fixed gate in the circuit that computes that function. So maybe this computes the first output bit, this computes the second output bit, maybe the third output bit is the same as the first output bit, and this guy computes it again, but that's what I mean by a circuit computing a multi-output function. And all right, so that's multi-output MCSP, and now I want to describe a little bit about how this reduction works. So it's going to be a reduction from set cover again to multi-output MCSP. And it's going to go in about 5 steps. So here the input is some set cover instance, S1 up to SM, that I'll say covers little n. And the first step is something I kind of glossed over when I gave the intuition for Oracle MCSP being NP-Hard, but it's something that needed to be done there as well, which was kind of randomize the set cover instance. So we're going to take these sets S1 up to SM, and we're going to kind of map them into a slightly larger randomized ground set. So now the ground set is of size capital N, and these things are kind of like randomized versions of that. In particular, this is going to preserve the optimal size of a set cover. It's done in a way like that. And so that was the first step. Then the next step is, mimicking again the Oracle MCSP thing. We're going to pick a random function of length n. And so this is going to be a random truth table. It has no dependence on the set cover instance. And now we're going to pick extra outputs. And this is going to work in kind of like the same way as the Oracle MCSP result worked, except now these things aren't going to be oracles. They're going to be extra outputs in our instance. So they're going to have that property that whenever you look at some set of indices that corresponds to a set cover, that's going to give you an oracle circuit for T of approximately like the size of the set cover. So again, we're just taking what were the oracles in the Oracle MCSP instance, and now we're going to use them as extra outputs. They're not going to be all our extra outputs, but they're going to be some of our extra outputs. Okay, and step 4 is where we get our extra outputs. Here we're going to add these new functions that I'll call G1 up to GQ, and they're going to be arrived at in a kind of funny way. What you're going to do is you're going to have some fixed naive multi-output circuit for computing T sub S1 up to T sub SM. So by fixed, I mean like before you even looked at S1 up to SM, you had some way to map map computing any multi-output function into like some naive circuit. Maybe it's like a DNF or something like that. You just have some fixed way of computing any multi-output function that's like could be very naive, like a DNF. So you're going to look at like this naive multi-output circuit for computing these guys, these extra outputs. And what you're going to do is you're just going to list off G1 up to GQ is going to be all the functions computed by some gate in this naive circuit. Now, if this was if it's not clear exactly what I mean, this definition is going to be made clearer later. I'm going to go over it again. But the takeaway is basically you're going to have some naive way of computing these T sub S1 up to T sub Sm. And these functions G1 up to GQ are going to be kind of like the intermediate computations one needs to make in that naive circuit. So now you had the, so now everything we've done is we've picked a random truth table. We've gotten these extra outputs that somehow correspond to the set cover instance. And now we've like listed off functions that correspond to intermediate computations in naive multi-output circuit for computing these guys. And then our last step is going to output the following value. It's going to output the complexity of computing T along with these extra outputs, along with these intermediate computations, minus the complexity of computing these guys without T. And yeah, it shouldn't be clear at this point like why this should work. That's what I'm going to talk about next. Great. So why does this work? So first of all, basically what's happening in step 1 up to step 3 is we're kind of mimicking the Oracle MCSP proof. In particular, by that result, we know that the optimal cover size of the set cover instance is approximately like the relative complexity of computing T given these oracles. So what we're doing in step 4 and step 5, what we need to prove, or what it suffices to prove, is that this quantity right here, 1, actually approximates the oracle circuit complexity, the relative circuit complexity of T given these oracles. Because if we were able to show that 1 approximates this, then that approximates the optimal set cover size, so we would be done. So in summary, what's happening is we mimic the Oracle MCSP proof here, and then we need to add on these like this kind of extra gadget here, which specifies intermediate computations, and then we're going to try and use this thing over here to compute the oracle complexity. Get something that approximates the oracle complexity, which approximates the optimal cover size. Okay, so now I want to say like why that thing that we're outputting should approximate the relative complexity of T given T sub S1 up to T sub Sm. Oh, I'm missing some primes here. Sorry about that. So imagine you were trying to come up with some way to use multi-output complexity in order to approximate relative complexity. So a natural guess for what you might want to do is like something that corresponds to kind of like the chain rule in probability or symmetry of information in Kolmogorov complexity, if you know what that is. And so that natural guess from the chain rule says that, well, the complexity of computing all these things together is approximately the complexity of computing the last few things and the first thing given the last things. And kind of informally, what this translation says is if you want to compute T and like all these other functions, or, you know, then the best thing to do is to compute those other functions first and then compute the first function, possibly using the other functions. So that's like, if this chain rule was true, that would be like a translation for it. But of course, the chain rule is false. Basically, like, the reason is that, like, first of all, you might not even follow this path, that like first you compute the T sub si's and then you try and compute T. But even if you followed that path, it's possible that like in computing one of the T sub si's, you could compute something that would be very helpful for T. And so it would be you would use that to help compute T instead of just using T sub si. And kind of the intuition for this like extra step of adding these intermediate computations G1 up to GQ is to force any circuit to compute the T sub SIs in a specific naive way. And if you compute it in a specific naive way, then we're choosing it in such a way that with high probability, those things don't help compute T. So what we're saying is, or the takeaway on the slide is, okay, here's like a good guess for what like might be a way to compute relative complexity using multi-output complexity. It doesn't work because along the way to computing these T sub SIs, maybe you could compute something that was helpful for T. And so the way we're going to get around this is by forcing it to compute the T sub SIs in a very specific way that actually doesn't help you compute T. And that's kind of like what the intuition behind what's happening when we're adding in these G1 up to GQ. I mean, it sounds very sketchy, and unfortunately, in the given time, I'm not able to give you all the details of how that work. And if you're interested in that, I'd recommend you look at Bruno Loft's talk. But I can tell you a little bit about how this forcing works and like what the idea behind this forcing is. And that's what I'm going to do next. So how exactly are we forcing you to compute the T sub SI in a specific way? I'll kind of give a toy example of how you can force things, and it's basically gives you the idea behind the forcing that we're using in our reduction. And it's something I gave a talk after my TCS Plus talk. Magdalene Dobson was telling me that I should name this lemma the Mr. Rogers lemma, so I've gone ahead and done that. And this is kind of like the key thing we use to do forcing. And I informally, say this lemma is what it means is that like you are the best at doing you, or at least circuits are the best at doing themselves. And what it says is that any circuit C is going to be optimal for computing its own computational history, with the caveat that the C can't have repetitive gates, and it'll be clear what I mean by that later. So what do I mean? So let's take any circuit C that computes T sub S1. It doesn't need to be an optimal circuit. It could be like a DNF. It could be something like extremely unoptimal for computing T sub SI. Let's just say there's any circuit. And what I'm going to do is I'm going to look at the following multi-output function that I call the computational history of the circuit C. So it's going to take n inputs, and it's going to have s outputs. And what each of the outputs is going to correspond to is what's computed by some specific gate in this circuit. So you get an input X, and maybe the first output will be like what the first gate outputs on input X, the second output will be what the second gate outputs on input X, and so on. So it's going to map the it's just going to tell you what the exact computational history is on that function. It's going to tell you exactly what all the gates on that input, It's going to tell you what all the gates output on that input. And now what I claim is, that this circuit C, as long as it doesn't have any repetitive gates, which I'll say what that means later, is going to be optimal for computing its computational history. And it's kind of easy to see that C is a circuit for computing computational history of C. So you get that the complexity, the circuit complexity of computing this computational history is at most S. And on the other hand, the complexity of computing this computational history must be at least S. And the reason for this is there's S outputs. So you're going to need at least S gates as long as there's like no gates in here that compute the same function. And that's what I mean. So C is optimal for computational history of C as long as there's no gates in C that are kind of repeated and they compute the same function. And so what this means is, if the takeaway from the Mr. Rogers lemma is that if you want to force a multi-output circuit to try and compute some function in a specific way, what you can do is choose the specific way you want it to be computed, and then require you to output the computational history along that specific way. And what that does is it actually forces the only way to really compute TSIP-SI optimally, when you have the requirement to output all this other stuff, is to just do the naive thing of computing it like C. And so that's the end of my talk, and I hope you enjoyed it. If you have any questions, feel free to email me or any of my co-authors, and we'd be happy to respond to you.